Okay, so calculus integrals 1, day number 2, Archimedes method of finding the area under a curvy curve. Why is it so much harder to find the area under a curvy curve? Because we can't use trapezoids or rectangles of any sort, right? So now the curve takes away the ability to use what we know in geometry, and now we have to use left-hand sum, right-hand sum, and do a little bit of limits with it. So I want you to follow along today as I do what I do. First thing is we want to talk about how the left-hand sum and the right-hand sum, they, as we send the number of rectangles in each of those sums to infinity, they converge upon the exact area underneath that curve. So you can see the left-hand sum obviously on the left and the right-hand sum on the right. Or excuse me. Yes, the left-hand sum on the left, right-hand sum on the right. And then we get this exact area as we send the number of rectangles to infinity. Now this number under here, the rectangle number, is going to be important today. What would be true about each of these widths? They'd all be equivalent, but each of the heights are dependent on the input in which we are plugging into our function. So today all we're going to do is take the sum of a bunch of base times heights. And then we're going to take the limit of that as n goes to infinity. And you'll see something cool. And that converges on this language right here. This integral symbol is kind of, it might remind you of an S that's been stretched out a little bit. All that is the sum of all of the widths times heights. So I'm going to work with the right hand, or the right edge here, for just a moment to show you this. If I have an interval here from 0 to 1, and I split that into n rectangles, okay, that means I'm going to split each of these up into n rectangles. So we would call this this little segment here the first 1 over n. Right, and then we'd have the second 1 over n, and the third 1 over n, and the fourth 1 over n, and then we'd have the fifth 1 over n, and the n minus 1 1 over n. And then, of course, this would be n over n, which would be 1. Okay, now this number, this 1 and 2 and 3, etc., going on down the line, that's probably going to be way too large there. Each of these numbers represents what we're going to call it K. And over here they use the letter I, but I don't like using the letter I just due to its value in the imaginary world. Okay, so the width of each of these rectangles would be 1 over n, and the height of each of these rectangles would be f of 1 over n times k. Right, so we'd have f of 1 over n, which would give us that height, this first height right here, and then f of 2 over n, which would give us that height, and f of 3 over n, f of 4 over n, f of 5 over n, f of etc. as we go on down the line. Okay, and we're going to add all those rectangles up, but before we do that, we have to take n to infinity. So we have to make those infinitely small, which is kind of a weird concept. So the area of this would be the width, or the base, times the height. So we're going to take 1 over n, which is the width, times f of what we'll call k over n. That'll give us the height of the first rectangle. Then we take the second and the third and the fourth, we sum them all up, and we get our area under the curve. Okay, that is a general. These 4 items over here, you guys, we could prove using proof by induction. I think we're all okay with the fact that the teacher is going to tell you that's true, and you're just going to nod. Is that all right? Okay. Oh, you want to do all 4 induction? All right, I'll do it tonight. I'll do it tonight. I'll have them. 2 for you, 2 for me. Which 2 do you want? Oh, you're so nice to me. Thank you. Appreciate that. 1 over n. Okay. Okay, so now our goal is, and what I'm going to do is I'm going to take the right edge method, okay, and I am going to take the limit as n goes to infinity and show you that that gives us the area under the curve. We could do both sides and show that it equals, but we're just going to do one side. Okay, so here we go. We're going to find the area under the curve 3x squared from 1 to 2. But before I do that, I'm going to find the area under the curve from 0 to 2. And I'm going to find the area under the curve from 0 to 1. And then what do you suppose I want to do with that? Subtract. Okay, so our last step will be to subtract. Okay, so this is going to get a little bit interesting here, but we're going to roll with it. Okay, so number of rectangles, and I'm going to kind of help you along with how I'm going to grade this on the test, because you will have one of these on the test. Number of rectangles will be n. Am I recording? Yes, good. Okay, width. What would be the width of one of these rectangles? Not 1 over n now. 2 over n, right? I'm taking 2 minus 0, which is the width of the entire interval, and dividing it by n. So I get 2 over n. That's my width. My height will be f of 2 over n times k. Okay, and k is going to be the number that I generate based on that right edge. So I'll have the first right edge, that'll be k equals 1. The second right edge, that'll be k equals 2, etc. Now what I want to do in this next step is I'm going to plug this into our function. Our function is 3x squared. So I'm going to plug in 2k over n into 3x squared. Okay, comfortable so far with that? Algebra would tell me that this would be 3 times, why is that a 2? That should be an n. Somebody should have stopped me. Okay, that should be an n. Algebra would tell me this would be 4k squared over n squared. At any point, stop me if you're uncomfortable with this, or maybe don't. Height. For any given height, I'm going to take 12 multiplied by k squared and divide by n squared. Okay, so there's my height. So far, so good? All right, so if I add all these up, let's take k equals 1 up to k equals n of width times height. Width, excuse me, that should be a 2 over n. Width times height. What is the only item that's changing within this summation? K. K is the only variable, right? K changes from 1 to 2 to 3 to 4 to 5 to 6, all the way up to n. Okay. But what I want to do with this is I want to send n to infinity. That's kind of nasty, isn't it? Okay, so Archimedes, I don't know when he lived. He probably lived in 1975, something like that. He was probably just crushing this in the 70s. You know, watching HR Puffin stuff or whatever that old show was, and just crushing some area under the curve. But what did he then do? Well, he now knows that n, you can take the limit as n goes to infinity of a polynomial. So watch what happens. We're going to simplify this. So k equals probably in the 70s during like maybe the 13th century or something like that. You said 87? Okay, cool. 280. Okay, cool. BC. Got it. Back in the 80s. Those days. Okay, so what can I take out? What can I take out of a summation or a integral at any point that I want to? What can I draw out of it? I can always draw out the constant, right? I can always draw out the constant. I keep the variable in. I can always take the summation of a variable and just take the constant out and then multiply afterward, right? So in this case, what is the only item that is a variable? We just talked about it. Okay, I'm going to keep k squared in. I'm going to pull everything else out. And then what you're going to see is that as I take the limit, as n goes to infinity, I'm going to pull out 24 over n cubed. And I'm just going to take the limit, or excuse me, the sum, as k goes from 1 to n of k squared. Well, on the previous page, we said, Victor said he was going to do this one tonight, right, Victor? Okay, so Victor, I need you to go back in your slides for a second and tell me what this thing equals. Right, what does this thing equal as n goes to infinity? Okay, except it's I on that previous page, I think. N times 2n plus 1 all over 6. Okay, cool. What I'm going to do is show you that this limit as n goes to infinity All I care about is the leading term in the numerator. Ben, you got a question? That was on the previous page. There's a couple of items that are given to you. That's not something you have to generate. Okay, that's not something you need to generate. This is given to you. Right, exactly. Luca. So as I look at the rest of this, my leading term is going to be determined by a couple of things. N, 2n, and n. And 24. So what's 24 times 2? 48. And what's n times n times n? N to the third. There's going to be a whole bunch of garbage after it, right? I don't really care about it. Because what I care about is the leading term on the top and the bottom. And as n goes to infinity, what will this thing go to? 48 over 6. Which is 8. Which is infinity tipped up sideways. Yes, Zane, thank you. So the area under the curve, right, this, ready? From 0 to 2 of 3x squared, we have to do from 0 to 1, and then subtract them. Now, I'm going to do the shortcut, and on the video that I made, I have the formal piece of it if you want to look at it. Okay? But if I were to do the antiderivative of 3x squared, this is a definite integral, so I don't need plus c, right? I have 0 and 2 as my limits. I would have x cubed, correct, from 0 to 2. And if I plug in a 2, I get 2 cubed. And if I plug in a 0, I get 0 cubed. And 2 cubed is 8. And 0 cubed is 0. Oh my gosh. Right? So that had to come from somewhere. It's not like, poof, this symbol, this integral symbol just showed up and someone was like, hey, by the way, just take the power, reduce it by, you know, whatever. That doesn't just like float out of like some unicorn's butt as they fart. Okay? This isn't sparkles and bunny rabbits everywhere. Something had to come from something. And Archimedes figured that out for polynomials. Archimedes. All right, so one more thing, and then I'm gonna give you some time to work, and I might do some other stuff here with U substitution in a moment. But how would this change for 0 to 1? Yes, I know I could take the integral from 0 to 1 of 3x squared and get x cubed, and I get 1, right? I get 1. But how would things change here? Do the number of rectangles change? No. Does the width change? Yes. Now it's 1 over n, right, instead of 2 over n. Now, the height will obviously change as well. I'll do 1 over n times k and plug that into f, which would be 3 times the quantity k over n squared, right? 3 input squared. So I'd get 3k squared over n squared, and then you start the process the exact same way. Now, on your test, I want to be very clear about this. You're going to get, okay, I talked said individual down from 8 out of your 30 points on this question. Okay, it was going to be 8 out of 30 points. I talked them down to 5 out of 30 points. Now I want to break this down for you, okay? I want to break this down for you. This right here, writing all of this out, is going to be 2 of those 5 points. Two out of those 5 points. We're going to get some practice with this. Okay, this is going to be 2 out of your 5 points. Okay, the next 2 points. The next 2 points are going to be right here. Okay, and then your answer is worth 1. This is going to, no, on your test. Test is next week, probably Wednesday or Thursday. And this will be 1. So your answer is worth 1. You guys, hey, if you can't do anything else, right, set the beginning part up. Set the beginning part up, you get 2 points. Then if you're really struggling, take the integral from 0 to 2. Find the answer, tell me the answer. And you'll get 3 out of 5. Okay? So I'm trying to give you some help there, okay, because I know it's been